Good afternoon, everyone. We're excited to talk about utilizing PLEXOS to quantify the impact of dynamic line rating today. So, first of all, let's introduce ourselves. My name is Nergui Rentsen. I have been working in the energy market modeling for about 2 years now. I have an academic background in applied and engineering physics, specializing in thermodynamics and mechanical physics. I have gained experience in energy market modeling, simulation, and integrated resource planning. All right, now let's turn it over to Shannon to take us her introduction.
Thank you, Nergui. As she said, my name is Shannon Dancler. I also work at Ulteig, specializing in utility resource planning and energy market modeling. My background is also in physics as well as electrical engineering with emphasis in the power systems and renewable energy technologies. At Ulteig, we are able to support nodal market analysis as well as integrated resource planning and capacity expansion efforts. I'm going to turn it back to Nergui to take us through our first portion of our presentation, and we're excited to present this research to you today.
Okay, thank you, Shannon. So, let me briefly walk you through today's agenda. First, we will begin introducing Ulteig and who we are and what we do. And then we will provide what the dynamic line rating is and importance of dynamic line rating. From there, we will discuss about the role of the dynamic line rating, and then this will be followed. We will discussing the data center growth and electrification. Next, we will look at the role of the PLEXOS and how we utilize PLEXOS in our study. After that, we will walk you through study details, then we will share the findings from the study. Last but not least, we will share what we're looking forward to next. So, before diving into today's main topic, let's give you a brief introduction of Ulteig, who we are. Ulteig is an industry leader in infrastructure engineering and technical service since 1944. Our expertise area include power, renewables, transportation, and water. So Ulteig has clients in public utilities, electric cooperatives, local, state, and federal governments, developers, and many more. So Ulteig has 2,500 plus projects each year across the United States and Canada. So we are 100% proudly employed by our 1,300 plus employees. So we have been utilizing PLEXOS for our energy market modeling study since 2021. Now, let's move on to the understanding the core focus of today's discussion, dynamic line rating. Grid enhancing technologies offer enhanced opportunity to improve the flexibility of the transmission system. One of the grid enhancing technologies is dynamic line ratings. Dynamic line rating adjusts the transmission line rating based upon ambient conditions such as temperature, wind speed, and electric configuration. So what is the benefit of the dynamic line rating? It can offer several possible benefits. First, reduce generation and load interconnection costs. And then, reduce generation curtailment. Finally, reduce transmission congestion. So now we have a grasp of what the dynamic line rating is. So, next, let's focus on the specific role of dynamic line rating. So, dynamic line rating allows increased transmission rating values, which enables greater power flow down the transmission lines. So, you might be wondering, why is it important to increase the transmission rating values? It is because when the shadow price, when the power flow on the transmission line reaches its rated capacity and non-zero shadow price emerges, leading to transmission congestion. In other words, shadow price is essentially a tolling charge for the traffic on the transmission line. By increasing the flow level before shadow price emerges or decreasing shadow price on the transmission line, congestion at the power node connected to that line may be lowered. As a result of increased transmission rating values, the shadow price may be lowered and congestion associated with the power node can be reduced. It is also possible that if the situation is severe, the output of surrounding power resources can no longer be adjusted to alleviate the transmission constraints. When this occurs, resources may be curtailed on the system to alleviate overload. It is possible if the generators can also curtail economically when redispatch leads to a severe economic penalty. As you can imagine, generation curtailment is also affected by dynamic line ratings. Increasing line capacity has potential to significantly alter the point the resources must be curtailed. In total, effect of this is to potentially allow for greater generator dispatch levels along with the generator and higher generator and load interconnection amounts. Interconnection studies are based on transmission ratings and contingencies. So raising the rating of the constrained transmission line can lead to expanded headroom for the interconnecting resources. In summary, utilizing dynamic line rating can enhance overall grid efficiency by reducing congestion, increasing transmission capacity, and lowering generation curtailment. Now, with a clear understanding of dynamic line rating, let's discuss about data center growth and electrification. So one of the main reasons we're interested in impact of the dynamic line rating is data center growth and ongoing electrification. So it is no secret that the rapid growth in energy demand from data centers and electrification across the United States is expected to continue. The talk of the energy industry right now is artificial intelligence and its large power needs. The expansion of AI technology requires significant computational power, which drives the more need for the data centers to handle the increased workload. The expansion of AI technology, like I said, although advancement in AI efficiency and truncated load additions due to supply chain challenges may lead to overstatement of forecasted growth, the amount of new interconnecting load still be significant. Likewise, the ongoing retirement of baseload resources is creating new as well as worsening existing reliability issues. Losing baseload generator is just as challenging as adding new load. The growth of these initiatives is causing significant stress on not only existing electric grid operation, but also on the need for additional power generation. Even some utility forecasts are predicting more than tripling their native electric load in less than a decade due to these initiatives. Now, Shannon will provide the detailed information about our study. Shannon, take it away.
Thank you, Nergui. Thank you. So, as Nergui said, now I'm going to walk through how we actually utilized PLEXOS for this analysis of dynamic line ratings on a transmission system, followed by our results. So, PLEXOS is an ideal platform to study something like dynamic line ratings because of its vast uses. It can be used for nodal market simulations, it can be used for probability or loss of load probability analysis, stochastics, capacity evaluation, and that list goes on and on. But for this specific research, we use the nodal market simulation capability of PLEXOS, which allowed us to do transmission-constrained production modeling of the transmission system. So from the vast outputs that come from a PLEXOS simulation, there are two metrics that I want to point out that are specifically relevant for this research. And before we dive into any more of the nitty-gritty details, I just want to define them explicitly so that we're all on the same page. Those are the curtailment factor and the congestion charge. First, the curtailment factor is approximately the capacity curtailed relative to the theoretical generation amount. Then, the congestion charge would be the sum of congestion charges for all relevant transmission lines associated with a single power node or a bus when there is a +1 megawatt injection at that bus. So what we're really concerned with here is seeing how adding another incremental megawatt at a bus affects the congestion charges for the surrounding lines, sum those up, and you get that congestion charge for that bus. This charge can be positive or negative, and a positive congestion charge would indicate that that generation resource is helping the system. And this could mean that your generation would result in additional profitability. On the converse side, we have if your congestion charge is negative, that would indicate that that generation is harming the system, and this could result in a reduction of profit for that generation. And I do want to know, as we're going along, if there's any topics that we don't get to discuss in enough detail for you or questions we don't get to, don't be afraid to stop us afterwards and have discussions with us about that. We'd love to get you the answers. So let's move right along into more of the details of this study. So in collaboration with Line Vision, Energy Exemplar, and the Purdue University Energy Efficiency Center, Ulteig produced this study that assesses the effects that dynamic line ratings have on a transmission system. This study utilized the PLEXOS 2024 Eastern Area Interconnection nodal data set, and to adequately study the effect that DLRs would have on a system, it's necessary to study a real system. To that end, we took a subset of the PJM system and used it for this test case. To capture the impacts of the data center load growth and renewable additions that we've been hearing about all morning, we built in a 1.5 gigawatt constant data center load, as well as a 1.5 gigawatt non-dispatchable solar resource into the model near the St. Joseph Energy Center in New Carlisle, Indiana. Now, you might be wondering, why was that area even chosen? Well, let's take a little bit of a closer look at the topology of that area. So first, the St. Joseph Energy Center has an existing gas combined cycle generator already in operation. There is also significant gas and electric transmission infrastructure available in that area. And there is an extra gas expansion port available at the St. Joseph Energy Center complex, which from our understanding, we believe there are plans for that to come online sometime later this year. So summing all of those points together, plus this energy complex's proximity to Chicago, make it a potential target for data center expansion. I do want to take a quick make a side note about this non-dispatchable solar resource. We built in a 1.5 gigawatt solar resource, which is pretty large, but we did this to study the effect of renewable generation on carbon offset. This was a purely speculative resource, not based on any site-specific information. So to determine the actual constructability of a resource like this, a site-specific feasibility study would be necessary first. Now, let's get back to our modeling. So we have the data center load built in, and we also have this solar resource built into the 2024 EIC data set. From there, we ran the simulation to identify some key binding constraints. The lines where those binding constraints were identified had the conservative static ratings that just come as default within the PLEXOS data set. So from there, we added a 10% dynamic line rating to that static value for those lines where we found the key binding constraints. We then monitored those lines to see if increasing that line rating would have any effect on the system. I do want to note that a 10% increase for dynamic line ratings is a little bit more on the conservative end of the potential line rating increase when utilizing dynamic line ratings, but for the purpose of this presentation and research, we felt 10% would be enough to be able to see the effects. We also did test higher cases in which the analysis and results for that is going to be published with the Association of Energy Engineers later this year, so keep an eye out for that as well. So, the results of the 10% DLR increase relative to the base case for this solar resource will be looked at in the next couple of slides. First, I'm going to walk us through a couple of the graphs that we got from the analysis, and then we'll go over some of the main takeaways and points. So, this first graph is going to be, again, for the non-dispatchable solar resource relative to the base case, and it will be for the curtailment factor reduction by month. In this graph, the blue bars are indicating the base case results where the lines where the binding constraints were identified had the static conservative ratings, and then our red bars are going to be for the test case in which we had added a 10% dynamic line rating to those lines. Overall, we can see a decrease in the curtailment factor when a DLR is utilized. And just as a reminder, again, the curtailment factor would be the capacity curtailed relative to theoretical generation amount. This would indicate that increasing the thermal rating on those lines significantly improved the ability for the solar resource to avoid curtailment. Which I do also want to make another note here is that even though the DLR did significantly reduce the curtailment amount, we can still see from this graph that there is quite a bit of curtailment left. But in this case, the point of our study wasn't to see how DLRs directly affected curtailment or congestion levels. If that was the point, we would want to reduce the size of the solar resource so that our primary factor was congestion rather than curtailment. But this is something that would lend itself to research in the future and a way to continue looking at this analysis. Our next graph here is going to be looking at the average congestion charge by month, again for the solar resource. And we see that during the summer and shoulder months, the case where the dynamic line rating was utilized resulted in a lower average congestion charge. And once again, harkening back to my definition of congestion charge, in those months, we do want to see a less negative number because that means that our generation is harming the system less. And as we can see, these results are not universal in that significantly decreased solar production in the winter months isn't really allowing us to adequately study the effect that the DLR had because our solar resource is in a northern climate, right? So if the solar resource had been in more of a southern climate where we didn't need to worry about like decreased winter solar production or different load aspects from the winter as we've been hearing about, it's likely that the DLR would have had a similar effect and impact as we see in the summer and shoulder seasons here. So as we keep moving on now, what are the absolute main summary points that we found from this analysis? It showed that dynamic line ratings can greatly reduce transmission congestion and curtailment, especially during those summer and shoulder seasons, especially in a northern climate. During those seasons, we saw that the curtailment factor reduction reduced beyond 50%. And again, as a reminder, we're interested in those months simply because that's when the non-dispatchable solar resource was generating the most, given where we modeled it within the system. During the summer and shoulder seasons as well, we saw the average congestion charge decreased overall. And I would like to emphasize that it shouldn't be assumed that DLRs will produce as significant an impact in all cases and simulations. This was just our first simulation analysis here. And additionally, operation restrictions beyond the theoretical line rating adjustments were not considered for this analysis. But that does point out something that we could consider for our steps in the future. How does Ulteig see this type of research continuing, or what do we want to look into next? So something that is an option for continuing this research would be looking at how DLRs operate from an hourly perspective. This would require using hourly or even sub-hourly data, which was not available at the time of this analysis. So what we did in the presentation and the results that we just showed you was we used an annual static dynamic line rating value based on input from line vision. And we did that in order to just create a bounding case and to test the annual version of this. Another way that DLRs could be studied in this vein of research would to see how DLRs affect grid reliability from an operation resource adequacy standpoint. So overall, next steps, we would love to look for partnerships with utilities to further this research so that we were able to explore the impacts of those hourly incremental data as well as operation restrictions as well, instead of just annual averages for the dynamic line ratings. With that, we just want to thank a few people first before we get to questions. We want to acknowledge Energy Exemplar for their collaboration and support in our use of PLEXOS for this analysis, as well as allowing us to speak at this conference today. And we also want to thank Line Vision and the Purdue University Energy Efficiency Center. So with that, thank you for listening to our presentation on how we can utilize PLEXOS to analyze the impact of dynamic line ratings, and we'll open the floor up for any questions.
Any questions, guys?
Hi, Nergui and Shannon. Great job. Amazing presentation. For someone else who's maybe looking to use PLEXOS to study dynamic line ratings, or is there any recommendations or lessons learned about your experience with using the PLEXOS model that maybe you could speak to your experience about a little bit through that process or timeline? Just kind of curious for your thoughts on that.
Thank you, Arthur. That's a good question. So first, I am just going to point out we do have another collaborator on this research. Dr. Andrew Kramer also works at Ulteig, and he was the primary modeling lead on this case. So he would probably have a plethora of things to comment on this. But I think a big thing for us, from my understanding, was identifying the key binding constraints, so being able to use the SCED portion of the PLEXOS analysis to identify which lines were causing the congestion issues, and then being able to adjust the ratings from there. I know that was an integral part of that and would be key to an analysis like this, so you're being able to utilize PLEXOS for that and having an understanding of that would be good. I think that might answer that, maybe not.
Yep, thank you. Another question?
Maybe I missed it during the presentation, but when you guys were talking about the prices you used, were you talking about, did you use historicals, or are you using projected forecast? Is it using LMPs from PJM or MISO? I'm not familiar which region this was associated in. I'm just kind of curious, what was the prices that were used on an hourly basis to come up with this model?
Thank you for that question. Yes, so what we didn't use any specific data. This was in PJM, so we were using PJM and the EIC data set for this. And As far as specific pricing goes, we used what was within that data set already, and for the dynamic line rating situation, it was just an annual average value that we used in place of that. So a lot of it was just default like system data from PLEXOS, which is why it would be curious or like interesting to continue using research that does utilize specific operational information, and we would love to do that in the future.
Awesome. One more question.
Thank you. Hi. Thanks for the great presentation. Great job. I just had a quick question on the actual implementation of the DLR. So was that just done to the normal rating, or did you make any changes to the, I know this differs from ISO to ISO, but the STE or the LTE or the rate B or rate C?
This is a good question also. I actually definitely know the answer to this. So for that, we just adjusted the like normal rating for it, and because we were just running things under system intact conditions, so we just adjusted that rating up 10%.
Got it. Thank you.
I think that's all the questions we have. Oh, one more.
This is great presentation. I'm just wondering, right now you use the EIC data, and how easy it is to do like this analysis in different regions or like apply to different areas?
So I think my first intuition on this would be that if you identify a similar area or an area that you would have of interest, so like in some of the maps and other presentations, we saw that there is like significant data center load growth coming in ERCOT. So doing a similar analysis in an area where we kind of know this is happening as well would be pretty straightforward, right? Just identifying lines or buses near that. So you would have to have some information where you are a little bit privy to the area that might be happening, which is why we did it in PJM. We're pretty familiar with like the Indiana area there around the St. Joseph Energy Center. So I would say that it would be like a medium level of ease to implement this depending on your knowledge of the area. Yeah.
One more.
Yeah, hi again. I just had one more question. Just taking a step back and really thinking about, DLR, I think we can divide the value in a couple different ways. This is more of a question about maybe what you found when you were doing some literature review. I think one, obviously I think that it has applications in the day-ahead market or maybe the real-time market, switched. But the other one I'm thinking of is as it relates to, and this would be a great question, I think, for the NERC gentleman here, but as it relates to how NERC and all these other kind of authorities are thinking about baking in dynamic line ratings into planning and other kind of frameworks. So just curious if you found anything interesting that you'd like to share there, or
Yeah, that is a really good question, actually. I specifically didn't find anything that stuck out to me, but I would also be curious about the same thing. So if I do find anything going forward, I'll be sure to let you know.